Okay, let's look at a simple pendulum to make sure everybody found the same thing in the lab. In this case, it's a simple pendulum consisting of my son and a swing. And so we're going to time 5 periods, starting there. And this is low amplitude. 2, 3, 4, 5. And so I got 13.8. You might hear him asking for too high is what he's saying. He doesn't like low amplitude. He likes to swing way up there. But when I do that for him, and his mother comes back and looks in the yard and sees me doing that, she will yell, "That's too high." And so he's learned to call that too high. And so she's not around when I'm filming this. So here we go, medium amplitude. Start it there. So 1, 2, 3, 4.
Okay, Daniel.
5. So he's still not too happy with the amplitude there, but we'll help him out in a second. And so I get 14.1 for 5 periods. So a little increase, it looks like. Let's see if that trend continues when we get him going too high. I started it there. 1. See, he's happy now. He's not complaining. 2, 3, 4, 5.
There you go again.
And so I got 15.4. So a pendulum is not a simple harmonic motion oscillator, otherwise the amplitude would not affect the period. And in this case, the amplitude is changing a lot, and it makes a noticeable difference. In the lab, you probably noticed an increase of maybe 0.01, 0.02 seconds, and that was for 5 times the amplitude. And so if we restrict the amplitude to small angles, then it turns out this effect is very small and we can neglect it depending on what your standards are. And in that case, we'd call it a simple pendulum. So a simple pendulum, the amplitude doesn't affect the period. So that is really what we're studying here, but it's good to know that it is more complex, and we'll see why that is later when we look at a simple pendulum in detail. So now we're going to do mass, and so we already have the low mass, and what I'm going to do is increase his mass. You might wonder how I'm going to do that, by about 50%, and time the period. And so here we go. So I'm putting a free weight in his lap. He likes to have toys when he swings. He does not like free weights. So you're going to hear him asking for his ball.
Good boy.
I started it when he was forward. 1,
The ball instead.
2,
Okay, just a minute. Count to 3.
3,
1,
4,
2,
5.
3.
And so we get 14.0. So it looks like it went up a little bit, but again, I'm just doing timing with a stopwatch. And if you increase something a lot and something doesn't change much, you want to look at it carefully before you say there's an effect. There is no effect with the mass. If you increase the mass, you increase inertia, but also you increase gravity, which is the restoring force. And so the accelerations don't change. We already learned that. And so neither does the period. And then finally, length. So we have the high length, 13.8 again. And the low length, how am I going to do that? It's the first time Daniel ever saw this. He's a little puzzled. And so I wrap the chain around, start it there. So he's looking up, he's like, wait, the ground's further and that tree is closer. Yeah, lose count. 4, 5. And so we do get 12.6, which isn't a big change. I didn't wrap it. I should have wrapped it more maybe. But you should have seen this in the lab. As you increase the length of the pendulum, period definitely goes up. And so you might think, well, that's the only thing that's going to affect it if we neglect the amplitude. Changing gravity also could affect it. And so that is difficult to do, but it would affect the period. So if you went up to great altitude, gravity gets a little weaker. That would slow the pendulum down because the inertia stays the same, but the force of gravity gets a little weaker. You could simulate it in an elevator. The elevator is accelerating upward when you feel heavier. That's like the gravity stronger, and the period of the pendulum would decrease. It would go faster, reducing the period. And if you were accelerating down when you feel sort of lighter, that's like decreasing gravity on the pendulum. It would go slower and it would increase the period. So one last final experiment here. We talked about resonance. When you force something to vibrate at its natural frequency, the period or the amplitude will increase. And in some cases, dramatically so. We saw the Tacoma Narrows Bridge oscillating up and down because of the wind. Here I'm giving him a push at the frequency of the pendulum, the swing, and his amplitude keeps going up and up. Question is he going to go all the way around if I keep doing this? So theoretically, the amplitude should keep increasing. I keep forcing it to go. Is it this next time? I think he goes around here. Nope. There he is. There. He went all the way around. Okay, let's discuss the pendulum lab here on the back page where Morton, Peter Fox's lab partner, is telling him to graph period squared versus the length. And so you should have done that on the computer. And you should have got a very straight line. When you hit the computer, do the best line fit. Your points should be pretty close to that. And then you're asked to get the slope. You can just use what the computer said. You go to analyze and do best line fit. You can use your calculator to get it. But this would be your experimental slope. And then you're asked to compare it to 4 pi squared over g. And 4 pi squared over g comes out to about 4.03. I think it's like 4.028 or something. And usually the data is really good. It's not unusual for a lot of groups to have under 1% error. If yours is kind of big, you might consider plotting your other data table because you had 2 data tables you could graph. But if it was, I don't know, within 0.1 or so, that's still not too bad. Then you're asked to write an equation for the period of a pendulum. And the key thing here is the theoretical slope. And so based on the graph, we can start with y equals mx plus b, and that's what you should do if you're showing your work. You're showing that. And then on your graph, well, what was y? It was period squared. And then what was x? Well, it was L. And then you think about what the y-intercept should be. Here I'm giving you some help, but the y-intercept is the period when there's 0 length. So you don't have a pendulum, there can't be a period. So theoretically, that should be 0. And then based on what you found out above, theoretically, 4 pi squared over g is the slope. So if I want to solve for the period of a pendulum, I can take the square root of both sides, and I get this. And so that is the equation given for the period of a pendulum. Now this is a simple pendulum. We're assuming that the amplitude doesn't affect the period. We're keeping the angle low. And again, we'll discuss why we can do that later. Some people were asking why period squared? Why did Morton say that? If you would have graphed just period versus the length, it still looks pretty straight for the range of data we collected. And so it would have been hard for you to see that it was really a curve. And then when you see a curve, you try things until you get a best line fit. Another reason to see why it's period squared is to look at the units. And so the units on this side, 4 pi squared, no units, but I have meters for length over meters per second squared for little g. And so the units are seconds squared, but period is just seconds. And so if we square the period, then we get seconds squared, which agrees with that. So then calculate your percent error after you figure out how long to make a 1 second period. So you could say 1 equals 2 pi square root of L over 9.8 and solve for L. Some people realize they could start with that and that'd be easier. I recommend you want to get used to this equation, so I would use this equation, but it's correct to do it the other way. And so question 3, if you moved one of your pendulums to the top of Mount Everest, what would the period change? If so, how and why? You should know that as you go up, little g decreases. And so if this gets smaller, you're dividing by a smaller number, the period would go up. And so it would increase, and the reason is gravity is weaker, and so the restoring force is less, but the inertia, the mass of your pendulum is the same. And question 4, if you went to an orbiting space shuttle with a pendulum, would the period change? If so, how and why? And the answer is yes, and it depends on exactly what you do. So here's your pendulum here, and so you're holding it, I guess, and you pull it back and you let go, and what does it do? Well, it would just stay there, so it'd be sort of undefined. But if you gave it a push, then it would go around in a circle, and the period would depend on how hard you pushed it. So it would no longer be an oscillating system, and so undefined, I think, is a good answer. As far as why, when I read this, a lot of times I'll see people will write something like it's there's no gravity, or it's microgravity. We'll find out where the space shuttle used to orbit and where the International Space Station is now. Gravity is about 88% of what it is here on the surface of the Earth. And so the reason this happens is the pendulum is in free fall along with the space shuttle. So if you were to hold your pendulum and jump off one of the tables as you let go of the pendulum, it wouldn't move either, at least in the short time you're falling toward the floor. And there's no difference between that experience and what's going on in the space shuttle, except the space shuttle's going fast enough sideways so that its path doesn't intersect the Earth. And your path will. So you experience this free fall for a shorter duration, whereas the space shuttle, as long as it's up, and the same with the space station, is in free fall. Okay, in the lab, you were challenged to construct a pendulum with a 1 second period. And so what would happen if we said you had to make a pendulum with a period equal to pi, since we just had pi day? And so if the period equals pi, what would the length be? And so we know the equation for the period of a pendulum, 2 pi square root of what goes on top? Well, it's what makes the period more. If you increase it, then it's L. What goes on the bottom? Little g. If the gravitational field strength is stronger, the restoring force is larger, bringing it back faster, shortening the period. So we just put in pi for the period, and maybe try doing this in your head. It's not too difficult. Remember, when we cancel the pi here, there's a 1. So I can divide both sides by 2. And now I can square both sides. And I get 1/4 equals L over G. So L is G over 4. And that is 2.45 meters, which just happens to be long, not too long for a classroom. And so here we have a pendulum set up in the classroom. The string is attached to the ceiling. The length is 2.45 meters approximately to the center of mass of the pi. and there's a flag hanging from the pi and a photo gate. And so let's see what happens here. There we go. So I'm getting pretty close. 3.12. You wait long enough, sometimes it makes it.
Pretty constant, huh?
So that is a pendulum made from a pi with a period equal to pi. So of course, that makes it a pi pendulum. And so to celebrate that, we wrote 3.14 on it with icing. Oh, wait a minute. We wrote pi on it. So if you look at it in a mirror, 3.14 spells pi. So coincidence? I think not. Okay, let's take a look at pendulums, but first a little review of a spring mass system, and we'll find that if we know that well, we can make analogies with the pendulum system as a simple harmonic motion system. So we have a mass on a spring, and it's on a frictionless surface. Spring constant is K, and we can draw a free body diagram if we want. And if I have to the right positive, and I extend the spring would be pulling back in the negative direction. If I compress the spring pushes back opposite to the direction of X. But usually we just say the force of the spring is Kx, and when we do a graph, we make it positive, but if you have to think about the direction of the spring, just think how springs work. And we can write out the period equation. Period is 2 pi square root of, well, we know it's m over k for a spring mass, but in general, it's inertia over the force constant. And so for a system that's going in a straight line, we know inertia is the mass, and the force constant is always going to be the slope of the force versus displacement graph. And we'll find out also if it's a rotational system, it'd be the torque versus the angular displacement. And so slope is the force constant. And so for a spring mass system, we replace inertia with m and the force constant with k, and that's our period. And then we know angular frequency is 2 pi over the period, the same equation as angular velocity. So if I put this equation in for the period, I get the angular frequency is square root of k over m. So you can actually remember this instead and then always solve for the period. And if some of the forces in the x equal ma, and again I'm ignoring the minus sign, there is one here. The x is always opposite to the direction of the acceleration. And I can solve for the acceleration, it's kx over m. And k over m we know is omega squared. If I squared this, I get k over m. And so that's sort of another way to derive the equation for period, is use Newton's second law either for linear motion, or we'll see this works for rotational motion, and set the force equal to ma, and then replace a with omega squared x, or whatever the displacement is. And now you can solve for omega, and for a spring mass system, it's square root of k over m, and that equals 2 pi over the period. So solving for the period, I get this. So we have two ways of coming up with the period of a spring mass system, or really any simple harmonic motion system. We have a generic period equation. It's always going to be 2 pi square root of the inertia over the force constant. And for a spring mass system, since it's just going back and forth, it's not rotating, the inertia is the mass. And then the force constant is always the slope of the force displacement graph. For a spring mass system, that's little k, so we get that. Or we can use Newton's second law, F equals ma, solve for a, and so if I solve this for omega, the x cancels out, and I get omega square root of k over m, and omega is 2 pi over the period, so I can also solve for the period. So knowing this will help us with the other systems, like a simple pendulum. And so I have a mass on the end of a string, some angle, pulled back some angle theta. Length of the pendulum is L, that'd be measured to the center of the pendulum. And just a little review about what a radian is. A radian is the ratio of the arc length to the radius of the circle. So you can see this is part of a circle. So I get this, and so I could also solve for the arc length, which would be the angle in radians times the radius, which is the length of the pendulum. And so that is the displacement in a simple pendulum. It's the arc length. So free body diagram, I have tension toward where the string is tied. I have weight straight down. This will be angle theta. And I make positive x the direction of the acceleration, of the tangential acceleration. We're not doing centripetal acceleration here. So sum of the forces in the x equals mg sine theta. And so right away we have a problem. It doesn't look like this is a simple harmonic motion system. For a spring mass, the force was a constant times the displacement. Here it's a constant, mg, times sine of theta. And we know sine theta is not a linear function. But for small angle theta, sine theta is almost, I probably should say almost, equal to theta in radians. And so if you look at a table, you can see at 5 degrees, there's no difference out to the 1,000th place. 10 degrees, there's 1,000th of a difference. 15, a little bit more, but still almost the same. 20, still pretty close, but starting to deviate. And then 25, getting further apart. So if you restrict your angles to small theta, and that depends on how much error you're willing to accept, theta in radians and sine theta are the same thing. Definitely within 10 degrees, that's a pretty good assumption. They usually say out to 20. There's no hard, fast rule. So that means I can replace sine theta with theta. And then up here, theta is x over L. So if I put that into there, I get mg x over L, and mg over L is a constant times x, just like the spring mass system. So now everything we did for the spring mass, we can use for the pendulum. I can graph force versus the displacement, the slope, and then instead of being little k, would be this collection of constants, the mass of the pendulum, little g, and the length. And if we want the period of a pendulum, if we use the generic equation for period, 2 pi square root of the inertia over the force constant, well, it's accelerating tangentially, so the inertia is the mass, and the slope is the force constant. And so if I replace inertia with mass, and I replace force constant with mg over L, the m's cancel, the L moves back up to the numerator, and I get the equation for a simple pendulum. You could also use Newton's second law, F equals ma. And so the force is mg over L times x. And so I set that equal to ma. And we know a is omega squared x. So the x's cancel, the mass cancels, and I get omega square root of g over L. We also know that's 2 pi over the period. Solve for the period, you get the same thing. And so you can solve for it 2 different ways. Okay, let's take a look at a physical pendulum. And so in this case, we have a rod, but it can be anything that has a pivot point that's off its center of mass, so that there will be a torque that makes it swing back and forth after you disturb it. And we define a distance h is the distance of the pivot point from the center of mass. I should say from center of mass here. And if we do a free body diagram, we have weight coming from the center of mass. There's a normal force where the pivot is, but we can sum the torques about that point, so it won't matter. And this angle theta would also be the angle between the rod, or whatever the object's axis is, and the weight. And some of the torques would be mg sine theta, because you only want the perpendicular component, times the lever arm, and we define the lever arm as the distance from the center to the rotation axis. So that would be lever arm L normally, but we're using the term H because it also has relevance with the parallel axis theorem. And so we can see this is a disturbing torque. It is not linear with displacement theta with the angle that I bring it back, but we just learned that for small theta, sine theta is essentially equal to theta in radians. And so I can simplify this as the torque is mgh times theta. You have to be careful here. Mgh is not potential energy. It is the weight times the lever arm, and then we have sine theta, which we've replaced with theta, so we get the torque. And so now I can make a graph, kind of like we were doing with spring mass system, where we did force versus x, or a simple pendulum, we did force versus the arc length x. Now we're doing torque, Newton meters versus theta in radians. And the slope of this line, as you can see over here, would be mgh, and it would be a straight line, at least for small angles out to 20, 25, 30 degrees, depending on how much deviation you're willing to take. And so we can get the equation for the period of a physical pendulum. If we go to the generalized equation here, instead of period is 2 pi square root of m over k, m is the inertia, k is the slope of our displacement versus force, or in this case, torque graph. So you could really call this a torque constant here, but we're just going to keep calling it force constant, the slope of the graph. And so slope is the torque constant, and inertia, since it's rotating, would be I. And so we have determined what the equation for the period of a physical pendulum is by using this relationship. There's another way to do it. Sum of the torques equal I alpha, and alpha is omega squared theta, just like A is omega squared x. And so I can replace alpha with omega squared theta, and I can replace torque with mgh theta that we got from up here. And so I can solve for omega, and I get square root of mgh over I, and omega is also 2 pi over the period, so if you solve that for period, you get the same thing as over here. Now I mentioned when we did simple pendulum that you could also treat simple pendulum this way, with torque equals I alpha. And if you do that, the I is for a particle, because a simple pendulum we don't have an extended object, so we just say it's mr squared, where in this case L is the radius of swing for a simple pendulum, and that is also the distance from the center of the simple pendulum to the rotation axis. And so I can put in ml squared and mgl instead of mgh into this equation, and the m's go and one of the l's go, and we get the same thing we got from our other treatment of a simple pendulum. And you can also do it using this same argument. Okay, here's an example of physical pendulum problem. We did this one in class, so it's kind of review. And so again, we're making a physical pendulum out of a rod, but physical pendulum could be anything, even you, if you hold really still. So anything that's pivoting back and forth is a physical pendulum. And we derived the period in the previous one, and so this is not on the equation sheet. You should know how to come up with it. It is okay to put it on your calculator in your calculator memory. It might come in handy if you know what it is, but you will need to show one way or another how you got it to get full credit. So in this case, I is the rotational inertia about the pivot point, not about the center. So we would need the parallel axis theorem to get the rotational inertia. And the rotational inertia of a rod about its center is 1/12 ml squared. And so that's what we'll use in I. So I is always going to be using parallel axis theorem for a physical pendulum, because if it was rotating about its center, it'd just spin. It wouldn't oscillate back and forth. There'd be no torque to bring it back. So we set the period equal to 2.5 seconds. We want to solve for h and the rotational inertia. is 1/12 ml squared, where L is 1. It's a meter stick in this case. And H is the same H as here. H is the distance from the center to the rotation axis. And so that's the H in the parallel axis theorem and the H in the denominator of the period equation. And so we simplify, the mass goes, and we put L equal 1. It's not always 1, so just be careful with that. And if we multiply that out, I divided both sides by 2 pi, and squared both sides, and you can see you get a quadratic, and you solve for H, and you get 2 positive answers. Which should we pick? Well, you can see clearly from the drawing here, and the fact that we have a hole in the meter stick, it's got to be this. This would be off the meter stick. It is true that if you were to hang the meter stick from a long string, and if this distance was 1.495 meters, it would have a 2.5 second period, which is kind of cool. Wanted to show something kind of cool I found out about physical pendulums. We were doing a physical pendulum example after deriving the equation for the period of a physical pendulum a few different ways. And a typical example problem would be find H on a meter stick so that the period is 2.5 seconds. And so H is the distance from the center of the meter stick to where we would put our pivot. In other words, where I would drill a hole so that when this oscillates back and forth, I'd have a 2.5 second period. And you go through the derivation or the solution, and you get that H is 0.056 meters or 1.495 meters. And the way the problem is written, where would you drill a hole, makes this the obvious choice. And so we reject the other solution from the quadratic. But it turns out with this system, that is also a valid answer. And so one year I just decided to try that out and see if it worked, and it turns out it does. And so I have a hole drilled on this meter stick at 55.6 centimeters roughly, and I've got a photo gate, and I'll start this oscillating, and I have it in pendulum mode, and I'm getting about 2.5 seconds, pretty close. And what I did is tied a string to the meter stick, and I have it pivoting on a magnetic hook on the ceiling, and the pivot is 1.495 meters from the middle. And so if you're careful when you start it, so the meter stick isn't doing this, but more of a nice back and forth without hitting the table. We do have small angle approximation. Let's try that again. So you can see these are one take videos. So 1, 2, let's get another one. So 2.52. So you can show them that you don't always reject both solutions in a quadratic solution. Like when you fire a projectile, what time is at a certain height above the ground? There are 2 answers to that. They have to think, oh, one's on the way up, one's on the way down. And this one has a solution too, which I thought was kind of neat, and maybe your students will too. Okay, let's take a look at another simple harmonic motion system. It's a torsion pendulum. Sounds like it's going to be more like a simple or a physical pendulum. It's actually got more in common with a spring mass system, and it is a true simple harmonic motion system, at least depending on what it is you're twisting. So we have some spring or a flexible rod, and I've attached a mass to it, in this case a disc, and if I rotate the disc a certain amount, the rod is bent and wants to go back to its original position, so if you let go, it'll oscillate back and forth like that. And if we were to measure the torque as a function of how much we rotated it, and this would be radians here, we would get a straight line, at least out to some point. Eventually you might break the thing, whatever it is. And the slope is kappa. Again, it looks a lot like K for a spring mass system, but this is torsion pendulum. So if we want to figure out what the equation is for the period of a torsion pendulum, again, think in general terms. on the equation sheet on the AP test, they give you the period is 2 pi square root of m over k. And when you see that, think inertia over the force constant, or the slope of a force displacement graph, or in this case, a torque angular displacement graph. You could call it, again, a torque constant if you want. And so the slope of the line is the torque constant, and the inertia is I because this thing is rotating. So it's 2 pi square root of I over k. Again, you should be able to derive this using this sort of general technique. You can also do it using torque equal I alpha like we did for physical pendulum. It is a good idea to have this in your calculator if you want, so you know what it is, but be prepared to show where it comes from. And so this is another way to show it. Torque equals I alpha, and so the torque is kappa theta. And so this is, again, the best fraternity to join, tau kappa theta. And alpha is omega squared theta, just like A is omega squared x for spring mass system. And so if we put this in for torque and this in for alpha, we get kappa theta is I omega squared theta, and thetas go, and you get omega is square root of kappa over I, and we know that's 2 pi over the period, so if you solve for the period, you'll get this. So two different ways of doing it. One, a sort of a graphical way of thinking about it, but once you derive what the torque is as a function of theta, you can come up with it. And so let's do a quick example. So we twisted a spring, so we didn't stretch it, we twisted it 100 radians, and it took 0.11 Newton meters to hold it. Find kappa. And so we're assuming 0, 0 is a point. Really, chances are if this was a free response, they'd give you a bunch of points of torque versus theta, and you do a graph and a best line fit. But this is a quick example, so we're just saying it's really the change in torque over the change in angle. And so this would be minus 0, minus 0. And we get 0.0011 Newton meters per radian. And so we have a solid cylinder. We're going to hang from it, 0.027 meter radius. And we twist it some amount. It doesn't matter, right? Because the amplitude doesn't affect the period in simple harmonic motion. And we release it, find the period. And so period is 2 pi square root of I over kappa. And I is 1/2 mr squared. No parallel axis theorem needed here. We're spinning it just about its center. It doesn't say anything different. I guess you could come up with a system that was somehow hung off center. I haven't ever seen that. It'd be hard to do, but you could definitely do it. That would be tricky. But so watch for that now that I've thought of it. But this is just about its center. And so we know the mass, we know the radius, we've already figured out kappa. We get 3.6 seconds, and then we did this in class. I had a spring in a cylinder that behaved this way, and it worked just fine. Okay, let's check out our prediction for the period of a torsion pendulum. So this is the 1 kilogram solid cylinder that we just used in our calculation, and this is the spring that we have the torsion constant for, and I obtained that by using this device called a torque check. And so this looks like a little drill bit end, the end of a drill. I attached it to the spring and twisted it, and then the amount of torque it took to hold it would show up here in ounce inches. So I had to convert that to Newton meters, and I'd twist it more and write it down, and we could do a graph just like we did in the lab, except in this case it'd be the torque versus the angle in radians. And so you saw that data, and so we've made our prediction, 3.6 seconds. So I'll twist it. Now you have to know what 1 period is. And so 1 period is from there back to where it started going in the same direction. So you have to watch it twist, stop, and then come back to the next time it stops. I'm going to start it now. So that's not a period. It's back to there. So I got 3.54. We could be a little more accurate if we measured more periods and divided by the number of periods, but that's still pretty good for checking out our equation.